This is Unit 6, Part 2, Periodic Table Notes. By the end of this lesson, you should be able to use the periodic table to identify and explain the periodic trends in terms of atomic radii, ionic radii, electronegativity, and ionization energy. Because the elements are arranged in increasing atomic number, or the proton number, there can be trends seen going across the periodic table and then going up and down. A periodic trend, in general, is just patterns of properties seen across the periods and within the groups of the periodic table. Recall that periods go from left to right and right to left, so they go across the periodic table, and the groups or families go up and down. So the first trend that we're going to look at is known as the atomic radius trend. The atomic radius, in general, is just defined as the size of an atom measured from the nucleus to the outermost electron. So if you look at the nucleus, and if you have the outermost electron all the way out here, the radius, again, is just half the diameter, so it's going from the nucleus to the outermost electron. If you go down a group, the periodic trend for atomic radius is going to increase. That is because the period number represents the number of shells around the nucleus. So in row number 1, we have 1 shell. Row number 2, there are 2 shells. Row number 3, we have 3 shells. So you can see as you go down a group, the size of the radius is going to increase, going from the nucleus to the outermost electron. And you can see a good representation of the atomic radius trend looking at the picture to your right. So again, as you go down the group, the size of the radius is going to increase. This also increases something known as nuclear shielding. So as you add in shells around the nucleus, you're adding a ring full of 8 electrons. So the more shells that you have, the more electrons you have, and then that's going to separate greatly the nucleus, the positive charge of your nucleus, from the outermost electron, and that's going to be important for something later on. So the more electrons you have shielding your nucleus here, so all this is shielding your nucleus, so it's blocking the interaction of the positive and the negative charge of your electron. So by increasing the nuclear shielding of the outer electrons, you're decreasing the interaction between the outer electron and the positively charged nucleus. Okay, so that's going down groups, and if you go from left to right across the periodic table, you're going to decrease the atomic radius as you go from left to right. This is because you're increasing the proton number. This is also known as the effective nuclear charge, or ZEF, Z-E-F-F. The Z represents the atomic or proton number, and the EFF is the effective charge. So by increasing the proton number, going from left to right within the atom, you're going to create a stronger pool of electrons within that nucleus. So go back to the picture at the top here. If we keep adding proton and proton and proton and proton and proton and proton, yes, you are adding electrons, but you are not increasing any more shells. So yeah, you're adding electrons around the outer shell, but you're also increasing the positively charged nucleus. So you're increasing what is known as the effective nuclear charge by increasing the proton number. And by increasing the proton number, you are creating a stronger pull of electrons towards the nucleus. And this is related to Coulomb's law, where you are increasing the force of attraction, which is going to create a shorter distance between the outer electron and the nucleus. So you're not affecting nuclear shielding as you go left to right across the periodic table, but you are increasing the effective nuclear charge, and then that also increases the Coulomb effect, where the stronger the interaction, the closer these electrons are going to want to get, and that's why the size is going to decrease going across the periodic table. So going down a group, the atomic radius is going to increase going down the periodic table, and it's going to decrease going from left to right across the periodic table, and that is the atomic radius. In comparison to the ionic radius, The ionic radius is defined as the size of the ion. So now we're looking at the ion radius size. So again, it's still measured from the center of the nucleus all the way out to the outermost electron, just like the atomic radius. But in this case, it's describing the ion radius instead of the neutral atom. Don't forget that ions are either going to be positive or negative depending on the addition or releasing of your negatively charged electrons. And if you look at the trend, it's still going to increase as you go down a group, and it's also going to decrease as you go from left to right. So the atomic trend is going to be equivalent to the ionic radius trend. They are the exact same, the fact that they increase going down and they're going to decrease going from left to right. Okay, and again, it increases going down just like the atomic radius because you're increasing the number of shells or energy levels as you go down the group or increase the period number. Okay, looking at the cation in comparison to the neutral element, cations are going to lose electrons to form positive charge, just like the T in the cation looks like a positive. So if you lose a negative particle, you become more positive. So looking at the structure of the Bohr model, if I were to kick off an electron from the group 1, because we talked about charges in the last lecture, it's going to lose that outer shell, and the size of that ionic radius is going to decrease because you have fewer electrons, and it's going to decrease the size by one shell. So every positive charge is going to decrease by a level of one shell because you're kicking off 1, 2, or 3 electrons in the outer valence shell. But the overall trend of going down the family or down the group, it's still going to get smaller just like the neutral atom. In this picture, the yellow is the neutral, and then the green is going to be your ion. So the cation in respect to the neutral is going to get smaller because you're losing electrons and you're losing an energy level or one shell around the nucleus. But going down a group, it has the same overall trend where they're going to they're going to increase going down the same family. Okay. On the other hand, anions are going to gain electrons to form negative charges. So if you gain an electron, you're creating a larger electron cloud because the more negatives that you put next to each other, they're going to want to repel each other. So the anion relative to the neutral atom, the anion is going to be larger in size compared to the neutral atom because you're adding in an electron and you're creating more electrons in that electron cloud. There's going to be a repulsion of those charges, and that's why anions are larger than the respective neutral atom. However, they all have the same trend. Going down a group, the size of the ion is going to increase because you're increasing the number of shells around the nucleus. And again, as you go from left to right, it's going to decrease in size because you're increasing the effective nuclear charge, so you're increasing your proton to your negative ratio. So you're increasing the proton to electron ratio. And just to overall sum up here on the the right side over here, both cation and anion radius are going to decrease going from left to right across the periodic table because you are increasing the effective nuclear charge, so you're creating a more positive to negative ratio, which is going to create that stronger pull. So you're increasing the pull of electrons towards the nucleus. So the biggest thing that you need to get out from this slide is that the atomic radius and ionic radius have the same trend, where you're going to increase going down, and then you're going to decrease going from left to right. You also need to understand that cations are smaller or have a smaller radius compared to the neutral, and that your anions are going to have a larger radius compared to the neutral atom because you are either giving away an electron to reduce the shells or you're adding an electron to create a larger electron cloud, as you can see in the anions, and then the cations whenever you lose that electron shell. Okay, so the last two trends that we need to learn about are electronegativity and ionization energy. These may be two completely new words for you, so it's really important that you pay close attention to these trends. Electronegativity is defined as the tendency of an atom to pull electrons towards itself when bonding with another atom. For example, if we had hydrochloric acid, HCl, these are two completely different elements, and they're not going to share the electrons within this bond very equally. Okay, that's because of an electronegativity. This chlorine atom has a higher electronegativity because it pulls the electrons towards itself whenever it makes a polar bond. That's because there is unequal sharing of those electrons. And the electronegativity trend is dependent on the radius trend. And just to recall the radius trend, as you go down, you increase the size of the radius. And then as you go from left to right, you're decreasing. So the trend is the smaller the radius, the stronger the electronegativity. So all of your elements that are up here in the right-hand corner have the smallest radius, so they're going to have the highest electronegativity. That is because you don't have a huge distance between the positively charged nucleus and the negatively charged electrons. Okay, the smaller that radius is, the more able that proton is going to be able to interact with other electrons of different atoms. And that's related to that electron shielding. So again, the smaller the radius, the stronger the electronegativity. That's because the smaller the radius, the less electron shielding there is. Thus, you allow a stronger interaction between the protons of the nucleus of one atom to the electrons of the completely other atom here. Okay, so this is opposite of the radius trends. So the smaller the radius, the larger the electronegativity. That's because you're exposing the proton, the positively charged proton of one atom, to the electrons of the different one. So the fact that this chlorine atom is very, 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 very small, the electrons are able to interact with the atoms or the electrons of the hydrogen and pull it closer to itself. So the smaller the radius, the higher the electronegativity. Okay. So that's your electronegativity, where you're pulling electrons towards yourself. Okay. And then your ionization energy. This is the energy required to remove an electron from the outermost shell of a neutral gaseous atom. Okay, so the ionization energy is the property of being able to pull off that last electron to form ions. So how able or how easy is it for this one atom to lose that electron to form a positively charged atom? Well, we already know that groups 1, group 2, and group 3 form +1, +2, and +3 charges. So groups 1, 2, and 3 are able to form those positive charges. So it might be very easy for them to lose those outer electrons. But think about the -3, -2, -1 groups over here. They don't form positive charges. They form negative charges, so they're adding in electrons. So it's probably going to be a lot more difficult for those atoms to want to lose electrons versus gaining them based on the charges that they form. So again, we can relate this ionization energy trend back to the radius trend. Okay, so the radius trend is extremely important, guys. Okay, so your atomic and your ionic radius, as you go down, you're increasing, and as they go from left to right, the radius decreases. Okay, so the larger the ionization energy is, that means it's more difficult to remove that ion. Okay, so the energy required to remove an electron, that is your ionization energy. So large ionization energy values mean that the electrons are very difficult to remove. So atoms with a large ionization energy values are going to have smaller radii or smaller radius. That's because the smaller the radius, the stronger this interaction between the positively charged nucleus and the outer electrons is going to be. So the smaller the radius, the higher the ionization energy. You have less electron shielding, and you have a larger attractive force between the positively charged nucleus and the negatively charged outer electrons. So it's going to require more energy to remove something that has a stronger attraction. So again, this is opposite of the radius trends. So what you should take away from this slide is, one, we need to know that the atomic and ionic radius trends are going to increase going down a group, and they're also going to decrease going from left to right. That is your radius trend. However, your electronegativity and ionization energy trends are the opposite. So as they go down, these are both going to decrease, and as you go from left to right, it's going to increase. So just recall the radius trends. Then you should be able to determine the electronegative trend, which is pulling electrons in, and then your ionization energy trend is taking electrons out of that outer ring, and they're opposite of each other. Okay, so this is the summary of the trends, which we've been talking about through the entire lecture. The atomic and ionic radius are going to increase going to the left and then going down. So the overall trend is going in this bottom left direction, while electronegativity and ionization energy are going to be increasing going into the top right direction. And just to describe the atom with the largest radius, that's going to be your francium here. This guy has the largest radius because it has 7 shells around its outer ring, and it has the lowest effective nuclear charge on every other element going across the periodic table. Fluorine has the highest electronegativity, and then your helium has the highest ionization energy. So those are going to be 3 elements that you need to memorize, where francium has the highest radius, fluorine has the highest electronegativity, and helium has the highest ionization energy. Okay, so then the overall trends, your radius increases going in the bottom left direction, and then your ionization energy and electronegativity are going to increase going in the top right direction. And all trends can be explained by 3 factors. Your effective nuclear charge represents the trends going across the periodic table. So as you go from left to right, you're increasing the effective nuclear charge by adding in more protons to electron ratio. You don't change any of the shells, so you're not affecting the electron shielding going across, but you are increasing the attraction between the more positives in your nucleus to the outer electrons. So going across the periodic table, that's related to your effective nuclear charge and your Coulomb's law, where you're creating that stronger attraction. Okay? Then as you go down a group, you're increasing size or the radius, but you are decreasing electronegativity and ionization energy, because as you go down a group, you're increasing the number of shells around the nucleus, so you're increasing the electron shielding. That way, the proton, the positively charged nucleus, does not interact with the outer electrons as much, so you're decreasing the attractive forces because you have all those electrons on the inner shells shielding that positive and negative interaction. So anytime you're asked to explain any of the trends, you should think about these 3 terms. You should think about the effective nuclear charge, where that relates to the proton to electron ratio within the nucleus. And then your Coulomb's law is describing the attractive forces between the outer electrons and the positively charged nucleus. So the stronger the attraction, the shorter the distance is between those 2 particles. And then your electron shielding is the related to the more electron shells. So if you increase the rings around the nucleus, you're creating a shielding effect between the positively charged nucleus and the negatively charged outer electron. So again, we need to understand the trends and then be able to explain using these 3 terms. All right, so let's practice a little bit of these trends. We need to list the elements in order from the smallest radius to the largest radius, and hopefully you can press pause, work these problems, and then turn it back on to see if you got these correct or not. But the first one, we have Rb, that's rubidium, I, iodine, O is oxygen, F is fluorine, and Sr is strontium. We need to list them from the smallest radius. So if we write R, radius, we're increasing going down and then decreasing going to the right. So the smallest radius, that would be your fluorine, because it is to the upper right hand corner. Oxygen is right next to it, going to the left direction, so it would just have a greater nucleus. I is all the way down on row number 5, so it's going to have 5 shells around it, which is going to be the third one. And then we're left with strontium and rubidium. If they're all in the same row, strontium would be the next largest one, and then rubidium would be the greatest or have the largest radius here. And that's because we're looking at this trend section right here. Now we need to list the elements in order from the largest ionization energy to the lowest. So ionization energy, as we go down a group, it's going to decrease, and as we go from left to right, it's going to increase. That's because it has the opposite trend of our radius. So it has the opposite trend, then the largest ionization energy is going to be in the upper right-hand corner. So fluorine would have the largest ionization energy. Then our oxygen would be the next one. Then iodine, then strontium, then rubidium. So here we have the largest to the lowest, or the smallest ionization energy. Then if we look at this back to number 1, we have the smallest radius to the largest radius. So the first one, we went from small to large. The second problem, we went from large to small. So what do you notice about the two trends? They are opposite of each other. Okay, that's because the larger the radius, the more energy it will take. The smaller the radius, the more energy it will take to remove that electron from that shell, because it's not going to want to leave it. Okay. Number 4 is asking about the trend for electronegativity. That's being able to pull in electrons towards itself. It relates to size. Okay, so it relates to size. If you have a smaller radius going from left to right across the periodic table, you're increasing the effective nuclear charge. You're also increasing the attractive forces that relates to Coulomb's law. Okay, and you're not affecting the electron shielding at all whatsoever. But for electronegativity, the smaller the radius, the stronger the attraction between the positive nucleus and the negative electrons that exposes the positively charged nucleus to interact with the other electrons in the other atom. And then if you go down a group, the electronegativity trend is going to decrease. That's because you're increasing the electron shielding around the nucleus to where that positively charged is blocked by all those inner electrons, and it's not able to pull in those electrons towards itself. So going from left to right across the periodic table, you should be able to describe that in terms of effective nuclear charge and Coulomb's law. And if you go up and down the periodic table, that relates to electron shielding and potentially the distance between the positive charge and the electrons of the other atom. Okay, so have you accomplished the objectives? Are you able to accurately use the periodic table to identify and explain the periodic trends in terms of atomic radius, ionic radius? Are you able to tell the difference between anions and cations, their radius in terms to the neutral atom? And are you able to identify the electronegativity trend and ionization energy trend? If you're not, or if you still have questions, I would rewatch this video or make notes of what to ask me in class whenever we go over this lecture.